Hello friends, I am Deepak Prajapati, welcoming you in lecture number 6 on random variables. In earlier lectures, we have discussed what is probability mass function and what is cumulative distribution function of a discrete random variable. In this lecture, we are going to do some more examples on probability mass function and cumulative distribution function of a discrete random variable. So let us start with first example. Before that, we can just quickly recall. Let capital X be a random variable which is discrete. Then PMF of X is defined as P of X equal to probability that capital X takes the value small x, and CDF is defined as f of x equal to probability that capital X observed value of capital X is at most small x, and this is defined for all real numbers. So with these definitions in our mind, we do some more examples. So first example, suppose at a fixed time we observe the gender of each newborn child at a certain hospital until a boy is born. So what is given? They are observing the gender of a newborn child at a certain hospital. So they are observing whether a newborn child is boy or girl, and they are observing the gender of each newborn child until they observe that the newborn child is a boy. Now it is given that probability of newborn child is a boy is small p, and also it is assumed that successive births are independent. That is, if first born child is boy, then the occurrence of second born child does not depend on the first born child. That means if first born child is a boy and the second born child is a girl, then they are independent events. So successive births are independent, that is assumption, and probability of a newborn child is a boy is given to be small p. So from this we can decide what is the probability that newborn child is a girl. So these two are complementary events, and so we can say that if probability of boy is small p, then probability of girl is 1 minus probability of boy, that is small p, and we assume that events are independent, and the random variable capital X is defined as number of births observed, and we have to find out the probability mass function and cumulative distribution function of this random variable. Random variable is defined as number of births observed. So what are the possible values of this random variable? So they are observing the gender of each newborn child until a child is a boy. So if on the first, or if the gender of first newborn child is girl, then the number of births observed, then if the first newborn child is a boy, then the number of births observed will be 1. Similarly, suppose the first born child, we can understand in this way. Suppose the first born child is a boy, then they will observe this gender. They will observe that the first born child is a boy, and they are observing until they see that the newborn child is a boy. So if the first born child is a boy, then the possible value will be 1, possible value of random variable. Random variable is defined as number of births observed. So they are observing the births until a boy is born. So if the first newborn child is a boy, then the possible value of x is 1. Now suppose the first newborn child is girl and second newborn child is boy. So if the first newborn child is a girl, then they will not stop observing, because they are observing until a newborn child is a boy. So if the first newborn child is a girl, they will wait for the second newborn child, and if the second newborn child is a boy, they will stop observing, because they want to observe the gender until a boy is born. So if the first born child is a girl and the second born is a boy, then the number of births observed will be 2. So in this way, suppose the first and second born children are girl and the third born child is a boy, then the value of random variable will be 3. So in this way, the possible values of random variable are 1, 2, 3 and so on. So there is no upper bound. Minimum value of x is 1 and it takes the positive integer values. So now we are interested in the probability mass function of this random variable, number of births observed. So by the definition we find out what is the value of probability mass function at x equal to 1. This suffix x denotes this capital X in the suffix indicates that this is the probability mass function of given random variable capital X. Because this small p is used for this probability, we have used this notation p suffix x. So p suffix x, this indicates that this is the probability mass function of discrete random variable capital X, which is number of births observed in this case, and this is by definition probability of the event capital X equal to x. So using this definition, x starts from 1, 2 and 3 and so on. It may take infinite number of values also. So first we will find out value of this PMF at some particular values, and then we will try to see whether we are getting some formula or rule to describe this probability mass function. So first we calculate, this is P of 1, that is probability of the event capital X equal to 1. Now capital X equal to 1 means this is the event that number of births observed is 1. So number of births observed is 1 if the first newborn child is a boy. So this is the probability that first newborn child is a boy, and it is given that probability of boy is small p. So value of probability mass function at x equal to 1 is small p. Now we check for x equal to 2. So p of 2 is by definition probability that capital X equal to 2. So this capital X equal to 2 represents the event that number of childs born are 2. That means 2 births are observed. So 2 births are observed, that means the second born child is a boy and the first newborn child is a girl. If the first newborn child is a girl, then only they will observe second born child, and if the second born child is a boy, they will stop observing. So capital X equal to 2 represents this event. First child is a girl and second child is a boy, and these two are independent events. This is probability of G into B, or you can write that this is the probability of these two events. You can write intersection also, probability of G intersection B, or we can write probability of G into B. And because these two events are independent, probability of G into B is nothing but probability of G into probability of B, and probability of girl is 1 minus P, and probability of boy is P. So value of probability mass function at x equal to 2 is 1 minus P into P. Similarly, we can find out value of probability mass function at x equal to 3. Instead of 2, we will have 3 births. So that is possible if the first 2 born children are girl and the third child is a boy. Okay, so that I have written here P of 3 equal to probability that capital X equal to 3. This is probability that first 2 children are girls and the third child is a boy, and these 3 are independent events. So probability of these 3 events, probability of this compound event, this is the intersection of 3 events. First is a girl intersection, second is a girl intersection, third is a boy. So probability of this event equal to probability of G into probability of G into probability of B. Again we are using the fact that these events are independent, and this is probability of G is 1 minus P, this is again 1 minus P, so it is 1 minus P square into P. Similarly, you can decide what is P of 4. P of 4 means we observed boy at 4th observation. Okay, number of births observed is 4 if and only first 3 are girls and the 4th one is a boy. If this happens, then only number of births observed will be 4, because we observe until we get that boy is born. Now again all these are independent events, so this is P of G into P of G into P of G into probability of B. Now probability of G is 1 minus P, and we have 1 minus P 3 times, so it is 1 minus P raised to 3 into probability of boy, that is P. Okay, so you can observe some common behavior for all these values. P of 1 can be written as 1 minus P raised to 0 into P. This I can rewrite as 1 minus P raised to 0 into P. And what is P of 2? We obtain that P of 2 is 1 minus P raised to 1 into P. Also we obtain that P of 3 is 1 minus P raised to 2 into P. Okay, you can see here P of 2 is 1 minus P into P, P of 3 is 1 minus P square into P, and P of 4 is 1 minus P cube. P of 4 is cube of 1 minus P. Raised to P. So from this we can generalize this. If I will have P of 5, then it will be 1 minus P raised to 4 into P. So P is there in each probability, and this is one observation. If we are calculating value of PMF at x equal to 1, then we have 0 here. So 0 means 1 minus P raised to 1 minus 0. Similarly, if we are calculating probability at x equal to 2, then it is 1 minus P raised to 1 into P. that is 1 minus p raised to 2 minus 1 into p. Similarly, we can say that p of 3 is 1 minus p raised to 3 minus 1 into p, and p of 4 is nothing but 1 minus p raised to 4 minus 1 into p. So in general we can say that if we have p of x, then power of 1 minus p is x must be x minus 1. So we get the formula for probability mass function. If you put x equal to 1 here, then you will get p of 1 equal to 1 minus p raised to 0 into p, that is p. If you put x equal to 2, you will get 1 minus p raised to 1 into p, so that matches here. Similarly, if we put x equal to 3, it is 1 minus p raised to 2 into p. So we obtain the formula for probability mass function. So we can say that the PMF of x is given by 1 minus p raised to x minus 1 into p for each x equal to 1, 2, 3, and for values which random variable is not taking, if x is any value different from these natural numbers, then px is 0. So in this way we can have the formula for probability mass function, and the random variable defined by this probability mass function is known as geometric random variable with parameter p. This is special type of random variable known as geometric random variable. Now once we have probability mass function, we can find out cumulative distribution function of the random variable using this definition. So using this probability mass function, we find out cumulative distribution function, CDF. So the CDF of random variable is given by f of x equal to probability that x is less than or equal to x. So it is by definition sum of all the values of PMF which are less than or equal to x. Okay, so it is like this. The random variable is taking the values 1, 2, 3. Okay, our random variable is taking these values, positive integers. So suppose x is somewhere here, then probability that capital X is less than or equal to x, this is will equal to probability that capital X equal to 1 or 2 or 3. So we have to add up to 1, 2, 3, 4, 5, 6, and all these are mutually disjoint events. Okay, this is x equal to 1 or x equal to 2 or x equal to 3 in that sense. So this is nothing but addition of all the probabilities up to x, p of 1 plus p of 2 and so on up to p of x. So we can say that it is summation of all the probabilities p of y such that y is less than or equal to x. In this case y is 1, 2, y can take values 1, 2, 3, 4, 5 up to x. So here summation of, we don't know where is this x, so we can write in this way, summation of all the probabilities values p of y such that y is less than or equal to small x. Now our function is p of x is 1 minus p raised to x minus 1 into p, and we are interested in p of y, so instead of x we will write y. So we put value of this p of y, it is 1 minus p raised to y minus 1 into p. Now the variable of summation is y, so we can take this small p outside summation because it is independent of y. So we are taking this small p outside summation in the next step. Now we expand this by taking different values of y. For y equal to 1, this is 1 minus p raised to 0, that is 1. For y equal to 2, it is 1 minus p raised to 2 minus 1, that is 1 minus p. For y equal to 3, it will be 1 minus p square. And similarly, for y equal to x, it will be 1 minus p raised to x minus 1. Now, to find out this summation, you can recall this formula. If we have 1 plus r square and so on, r raised to r n minus 1, it is geometric progression where r is common ratio. This is given by 1 minus r raised to n. If power is n minus 1, here we consider n minus 1 plus 1, that is n, divided by 1 minus r. So if we compare this with this formula, instead of r we have 1 minus p, and instead of n we have x. So this is, we put r equal to 1 minus p and x equal to n in this formula. So it is 1 minus p raised to x divided by 1 minus p. And here 1 will cancel out, so we obtain small p. And this small p will also cancel out. So finally it is 1 minus p raised to x, where x is natural number. So for values of capital X which are natural numbers, f of x is given by this. Here x can take the values positive integers 1, 2, 3, 4 and so on. Now suppose x is say 5.7. So if x is 5.7, then by definition f of 5.7 is nothing but probability that x is less than or equal to 5.7, but x is taking only positive integer values. So this I can rewrite as x is less than or equal to 5, that is f of 5. So in this way, suppose I have any natural number between 5 and 6 which can be equal to 5 also, then f of x will always be equal to f of 5. This we have discussed in earlier lecture also. Okay, if x is any integer between 5 and 6, then value of function becomes constant between these two positive integers. So CDF is always constant between any two positive integers, and it has a jump at every positive integer. So we use this fact. We know that CDF, that is fx, is constant in between positive integers. So and if x is less than 1, 1 is the minimum value of random variable capital X. So if x is less than 1, CDF is 0. This we have discussed in earlier lecture. If the value of random variable is strictly less than minimum possible value of random variable, then CDF has value 0 for all those values of random variable. So here minimum value of random variable starts from 1. So if x is less than 1, we can write capital F of x equal to 0. So for every x which is strictly less than 1, fx is having 0 value. And if x is greater than or equal to 1, means x is any real number greater than or equal to 1. So we write this in this form: 1 minus p raised to x. So this capital this is the integral part of x. This means the largest integer which is less than or equal to x. suppose my x is somewhere here, and suppose here the integer values are 3, 2, 1. Then this integral part of x means the largest integer which is less than or equal to x. So you have to concentrate on the integers which are less than or equal to x. So these are the integers which are less than or equal to x. Among these integers, 3 is the largest integer. So if x is somewhere between 3 and 4, then this is going to be 3. And if x equal to 3, then it is always 3. So if x is integer, integral part of x is x itself. So it matches with this formula. If x is natural number, then integral part of x is going to be small x. If x is natural number, because this is by definition largest integer less than or equal to x. So if x is integer, then it will be equal to x. But if x is any integer between two, if x is any real number between two positive integers, then we have to use this formula. So as I discussed, if I have to find out f of 5.7, then it will be 1 minus p raised to integral part of 5.7, that is 5. Integral part of 5.7 is nothing but the largest integer less than or equal to 5, that is 5. So it will be 5. So this is integral part is written because to find out the value of CDF at each real number. So here we have written this is the largest integer less than or equal to x. So finally the CDF is given by this formula, fx equal to 0 if x is less than 1, and if x is greater than or equal to 1, fx is 1 minus p raised to integral part of x, or in greatest integer function. Next example, we have given the probability mass function of a random variable by this formula, p of x equal to c into lambda raised to x divided by x factorial, and the possible values of random variable are starting from 0, 0, 1, 2, and there is no upper bound, and this lambda is some positive constant. So using this probability mass function, we have to decide probability of these two events, capital X equal to 0 and capital X greater than 2. So you can see in this probability mass function, this is unknown quantity c. So first we have to decide what is small c in this probability mass function. So how we can determine the value of c? So we have to use property of probability mass function. It is given that this p of x is a probability mass function. So we know that if px is a probability mass function, then the sum of all the values of px must be 1. So using that property, we will be able to decide what is this constant c. So first we find the unknown constant c in probability mass function using this fact. Summation of all the possible values of probability mass function must be 1, because this summation is nothing but summation of all the possible events. And here x is starting from 0, there is no upper bound, so summation is running from x equal to 0 to infinity. Then we have written value of px. Px is c lambda raised to x upon x factorial. X runs from 0 to infinity. Now in this summation, c is independent of x, so we can take c outside. So this can be rewritten as c into sigma x equal to 0 to infinity lambda raised to x divided by x factorial, and this must be 1. Now we expand this by putting x equal to 0, 1, 2. We write few terms. So if I take x equal to 0, it is lambda raised to 0 upon 0 factorial, that is 1. If I take x equal to 1, it is lambda raised to 1 upon 1 factorial, so it is lambda For x equal to 2, it is lambda raised to 2 upon 2 factorial. For x equal to 3, lambda raised to 3 upon 3 factorial. So we have this infinite series. Now if you recall this important series from calculus, the Maclaurian series of e raised to x. E raised to x can be written as 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Or the sum of this series for any value of x is e raised to x. Now instead of x we have lambda. So if you compare this with this series, 1 plus lambda square, if you compare this series with this series, you will get lambda equal to, in this series you will get x equal to lambda. So if we have x, we have e raised to x. So if we have lambda, it will be e raised to lambda. Okay, this series is convergent to e raised to x for all values of x. So lambda is also real number, so we can take x equal to lambda. So c into e raised to lambda is 1, therefore c equal to 1 upon e raised to lambda, and this we can rewrite as e raised to minus lambda. So we put value of c equal to e raised to minus lambda in this. So p of x will be e raised to minus lambda raised to x upon x factorial. X runs from 0, 1, 2 up to infinity. So once we have probability mass function, we can decide the different probabilities. So by definition, probability of capital X equal to 0 is nothing but value of probability mass function at x equal to 0. So here we put x equal to 0. E raised to minus lambda is constant. This is going to be lambda raised to 0 upon 0 factorial, and 0 factorial is 1. So we have e raised to minus lambda. Probability of this event capital X greater than 2. So here we are using the fact that capital X greater than 2 and capital X less than or equal to 2 are complementary events. So probability of this event is nothing but 1 minus probability that capital X is less than or equal to 2. And the possible values of x are 0, 1, 2 and so on. So if I consider capital X less than or equal to 2, then the possible values are 0, 1 or 2. So this is nothing but probability of capital X equal to 0 plus probability of capital X equal to 1 plus probability of capital X equal to 2. Okay, here we are using the fact that all these events are disjoint events. So this we can rewrite as value of PMF at 0 plus value of PMF at 1 plus value of PMF at 2. This is by definition of probability mass function. And finally by putting small x equal to 0, 1, 2 in this formula. If I take small x equal to 0, I will get e raised to minus lambda. For small x equal to 1, it is e raised to minus lambda into lambda divided by 1 factorial. And for small x equal to 2, we obtain e raised to minus lambda square upon 2 factorial, that is 2. And we can expand this bracket, so this can be rewritten in this form. So this is the probability of capital X greater than 2. And the last example of this lecture, what is given: a branch of a certain bank in New York City has 6 ATMs. There are 6 ATMs in some branch of New York City. Now what is random variable? Random variable capital X represent the number of ATM machines in use at a particular time of a day. Capital X is the number of machines in use at a particular time of day, and there are total 6 ATM machines. So what are the possible values of this random variable? So it is possible that at a particular time of day no machine may be in use. So there are 0 machines in use at a particular time of a day. There are chances that there may be 1 machine in use or 2 machines or up to 6 machines. So the possible values of random variable are small x equal to 0, 1, 2 up to 6. Okay, because there are 6 ATM machines. So we can say that the possible values of random variable are starting from 0, or we can write all the possible values 0, 1, 2, 3, 4, 5 and 6. So this you must be able to decide whether you require it or not. You must be able to understand what is the range of given discrete random variable x. Here the range consists of these 7 values, 7 integer values. Because there are 6 ATMs, these are the possible values of number of machines in use at a particular time of day. Now what is given? The cumulative distribution function of capital X is given. So you can see there are 6 possible values. So we have 0, 1, 2, 3, 4, 5 up to 6. So CDF of a random variable capital X is given. Probability mass function is not given, but cumulative distribution function is given. If x is negative, it is 0 and this must be 1. And using this cumulative distribution function, we have to calculate all these probabilities. So without finding out probability mass function, we can use properties of CDF to find out all these probabilities. Okay, if you recall that one property, if I want to find out probability of this event x equal to a, then if you recall the properties of cumulative distribution function which we have discussed in earlier lecture. Suppose this is small a, which is integer, then a minus 1 is also integer. So we can say that the event x less than or equal to a can be written as union of these two events. Which two events? X is less than or equal to a minus 1 union capital X equal to a. The event x less than or equal to a is the union of these two events. Okay, we are going up to x less than or equal to a. So we first write down this event x is less than or equal to a minus 1, and there is no value in between because capital X is discrete random variable. So another event is x equal to a. So probability of x equal to a is nothing but probability of x less than or equal to a minus probability that capital X is less than or equal to a minus 1. Okay, because these two are disjoint events, so probability of this event is nothing but probability of this event plus probability of this event. So probability of this event is probability of this event minus probability of this event. Now what is this? This is by definition f of a, and this is f of a minus 1. So you don't have to remember these formulas. You can always write them using this logic. Okay, so we are writing that formula. Probability that capital X equal to small a is nothing but value of CDF at a minus value of CDF at a minus 1, and we are asked to find out probability that capital X equal to 2. So probability that capital X equal to 2 is f of 2, here a equal to 2, so f of 2 minus f of 2 minus 1, that is f of 1. And now we can find out f of 2 and f of 1 from this CDF. F of 2 means we have to find out probability at x equal to 2, that is 0.39, and this is value at x equal to 1. So f of 2 is 0.39 minus f of 1 is 0.19. So 0.39 minus 0.19, that is 0.20. Okay, so without having value of PMF, we are able to decide these probabilities using CDF, that is cumulative distribution function. Similarly, probability of this event capital X greater than 3 is nothing but 1 minus probability that capital X less than or equal to 3. Okay, why? Because these two events capital X greater than 3 and capital X less than or equal to 3 are complementary events, and this is by definition f of 3, and f of 3 is given to be at x equal to 3, it is 0.67. So we put 0.67 and the required probability is 0.33. Next event is 2 less than or equal to x less than or equal to 5. So this we have discussed in earlier lecture. Probability that small a less than or equal to x less than or equal to b is nothing but f of b minus f of a minus 1. Okay, let us recall it again so that you don't have to cram the things. We have, suppose a and b are two integers and our x is in between a and b. Then you can see the event x less than or equal to b is the union of these two events. X less than or equal to b is the union of these two events. Suppose this is a minus 1. So I consider these two events x less than or equal to a minus 1 and this event a less than or equal to capital X less than or equal to b. Okay, if you can understand this, you don't have to remember this. Here the values are integer values, and we are interested in this probability that capital X lies in closed interval a to b. So we consider this event capital X less than or equal to b. This event is union of these two events capital X less than or equal to a minus 1 and capital X lies in closed interval a to b. Okay, there is no value which x assumes between these two integers. So x is less than or equal to a minus 1 union x is in between a and b including a and b. So from this probability that capital X less than or equal to b is addition of these two probabilities, and therefore probability of this event is nothing but f of b minus f of a minus 1. Here it is x less than or equal to a minus 1, so we have to subtract a minus 1. So using this logic, here if you compare with a and b is 5, so f of 5 minus we have to consider f of 2 minus 1. So it is f of 5 minus f of 1, and putting values of f of 5 and f of 1. F of 5 is 0.97, f of 1 is 0.19. So it is 0.78. Now if we consider this event 2 less than x less than 5, then x is less than 5 means the possible value of x is less than or equal to 4. Because of strict inequality, x can never be equal to 5. Now here we are using this property. Probability that a strictly less than x less than or equal to b is f of b minus f of a. So it is f of 4 minus f of 2, and values of f of 4 and f of 2. F of 4 is 0.92 minus f of 2 is 0.39. So it is 0.53. This also I have explained in previous lecture. If you don't want to remember the formula, you understand this. Our x is in this interval a to b. So we are considering these two events. X less than or equal to b can be written as union of x less than or equal to a and a less than capital X less than or equal to b. Capital X less than or equal to b is the union of these two events, x less than or equal to a and a less than x less than or equal to b. So probability of this event is nothing but addition of probabilities of these two events because both are disjoint events, and then you can write this formula. So you don't have to remember the things, try to understand in this way. So this is about today's lecture. I hope you like this lecture. If you like this lecture, you can write in the comment section. Also you can write your feedback in the comment section and share this channel with your friends. Thank you very much.